This is section 10.4, areas and lengths in polar coordinates. So the idea is that we're looking for the area of this region, which is, this graph is in polar coordinates. So here's a Riemann sum that we're looking at, and it's just a sector. And this is the area of a sector. And this can be turned into an integral. And it's just 1/2 times the function squared with respect to theta. And because we're in polar equations, the function is usually written in R form. So you can write it in this form if you'd like, or this form. It doesn't matter. So the first example says find the area of the region that is bounded by the curve. Here's the curve. And they give you the bounds. All right, so we can just apply the formula from the very beginning. You don't even have to graph this. This is A equals, we're going from 0 to pi over 6. 1/2, which I'll write outside of the integral, and it's going to be cosine squared theta because of the squared with respect to theta. So we can use the identity. Remember, the identity for cosine squared is 1/2 parentheses 1 plus cosine 2 theta. That's one of the identities that we know and we can use whenever we have cosine squared. All right, the 1/2, I'll bring that outside, so now it becomes 1/4, 0 to pi over 6, 1 plus cosine 2 theta, d theta. The antiderivative will be theta plus 1/2 sine 2 theta from 0 to pi over 6. And if you evaluate that, you should get, let's see, you're going to get 1/4, and then you're going to get pi over 6 plus radical 3 over 4. We don't have to plug in the bottom limit because that's 0, and then sine of 0 is 0. So we only had to plug in the top, and that's where I get this value for that. And when I plug in that, I get radical 3 over 2. However, there's a 1/2. That's why it becomes a 4. So our final answer, if we were to distribute, the 1/4 will be pi over 24 plus radical 3 over 16. That is the final answer. The next example wants us to find the area of the region that lies inside the first curve. So here's our first curve, which is a circle, and outside the second curve, which is a cardioid. So you can use Desmos.com again to graph these, to help you graph. So I'm going to draw a sketch of what that looks like from Desmos. All right, so this graph here is a circle, and it looks something like that. And this graph over here is a cardioid, and it looks something like this. All right, and then we're going from, so we need to find the points of intersection. That's important. So we need to find these 2 points, 1, 2. That's where the intersections occur. And to do that, you just need to set the two equations equal to each other, since they're both equal to r. 3 sine theta equals 1 plus sine theta. If you subtract one of these signs to both sides, you're going to end up with 2 sine theta equal to 1. So sine theta equals 1/2. And we know from our unit circle that sine has a 1/2 value at angles. What is it? Pi over 6 and 5/6 pi. Yes, pi over 6 and 5/6 pi. That's where these 2 points of intersection will occur, as you can see. So that would be pi over 6. And that would be 5/6 pi. And so now we know our limits of integration. So they want the region that's bounded between those two. So inside the circle and outside the cardioid would be this region. All right, and we're going to use the same formula. However, since we want a region that's between two curves, we have to do the subtraction. So it's going to be, and one other thing, you could either have your integration limits go from pi over 6 to 5/6 pi, or because of the symmetry here, you don't have to do all the way. You can just go from this to this and multiply by 2. So that's what I'm going to do. I'm going to go to pi over 2 instead of going all the way, because this is equal to that, which makes this symmetrical. So I'm going to go from, sorry, not 0, pi over 6 to pi over 2, and I'm going to multiply by 2 because there's 2 of those. So I'm just using symmetry. All right, so the formula says 1/2. So 1/2 r squared. So r squared, you have to do the top function minus the bottom function. So the top function is this one. So it's going to be 3 sine theta squared minus the bottom function, which is a cardioid, 1 plus sine theta squared, all with respect to theta. All right, so this is going to require some simplifying. So once you simplify, you should get all the way down to this point where you're going to have 8 sine squared theta minus 2 sine theta minus 1 d theta. All right, and then we have to use our identity. So remember, the identity for sine squared is this. 1/2 1 minus cosine 2 theta. So I'm going to replace this with this, and I'm going to simplify. So this after you simplify, you should get, let's see, you will get negative 2 sine theta minus 4 cosine 2 theta plus 3 d theta. All right, and then the antiderivative will be 2 cosine theta minus 2 sine 2 theta plus 3 theta. And we're going from pi over 6 to pi over 2. And once you evaluate this, and then you plug in the bottom one as well, and you subtract, you should end up with your final answer of pi. All right. The final question is asking us to find all the points of intersection. So in order to find the points of intersection, I highly recommend that you graph this. And once again, desmos.com is a great way to do that. So I'm going to copy what the graph looks like. So this will be my blue and this will be my red. So let's see. It's going to look something like this. You got these petals. All right, and then the other one will look something like this. All right. So once you got that, then you'll see that there are 3 points of intersection. There's one that's here, one that's here, and one that's here. All right, so that's very helpful to know, because then you know how many coordinates to expect. So the way you find the points of intersection is you can set these two equations equal to each other because they're both equal to r. So you have cosine of 3 theta equals sine of 3 theta. And now you can divide by cosine 3 theta to both sides in order to get an equation that we can solve. So that's just going to be tangent of 3 theta equal to 1. So we know from our unit circle that the tangent has a value of 1 at 2 angles, pi over 4, and also 5/4 pi. But since 5/4 pi is directly across from pi over 4, you can write this equation by just simply adding pi n. Any multiple of pi will get you to the opposite side. So now all you got to do is divide by 3, and that's going to give us theta is equal to pi over 12 plus pi thirds n, where n is an arbitrary integer. So if you plug in 0 for n, you're clearly going to get pi over 12. If you plug in 1 for n, you're going to get 5/12 pi. And if you plug in 2 for n, you're going to get 9/12. And 9/12 simplifies to 3/4. All right, so I did n equals 0, 1, 2. And I only went up to 2 because there are 3 points of intersection, so there it is, 1, 2, 3. That's why I stopped at 2. All right, so now we have our angles, and you can verify that. The first angle is pi over 12. That would be in quadrant 1. That would be this angle right there. So that's where the first point occurs of intersection. This 5/12 is actually close to 6/12, so it's also going to be in the first quadrant. It's going to be about right here. So for that, we're going to need a negative r in order to get to the opposite side. So this is going to require a negative r, so it's going to be this point right here. And then the final one is 3/4 pi, which is in the second quadrant right there. All right, so the polar coordinates should always be r comma theta. So we know there are 3 of them. I'll just write them up here. So for this one, we said the angle is pi over 12. And the radius, or r, would be, you can plug it into either of the 2 equations. It doesn't matter. I'll just plug it into the first one. So if you plug in pi over 12, you're going to get r equals cosine of 3 times pi over 12, which is the same thing as cosine of pi over 4, which is radical 2 over 2. So that's one answer. This one, let's do this one next. That would be 3/4 pi. So 3/4 pi, if you plug it into the same equation, you're going to get You're going to get 9/4 cosine of 9/4 pi, which will be the same thing. It's a coterminal angle to pi over 4, which is going to be radical 2 over 2 again. And then the last one is the one down here. So that would be 5/12 pi. And if you plug in 5/12 pi into the same equation, you are going to get cosine of 5/4 pi, which is going to be down in the third quadrant, and that is negative radical 2 over 2. And there's that negative that we were expecting. And the negative is there because 5/12 is actually in the second quadrant, and so you need a negative r in order to get to the third quadrant. So that makes sense. So that concludes the section.